meaning that from the point of view of some external observer of a transaction, there was a point in time before which the effects of that transaction hadn't happened, and there's a point of time after which its effects are completely visible. Okay? And even if the system crashes in the middle of running one of these transaction things, it's going to be, when it comes back from that crash, it's going to be either the effects of that thing will be completely reflected in the state of the system, or they won't be reflected at all. Okay. Consistency is sort of the kind of weird one here. We're not going to spend a lot of time talking about it, but in databases, typically what consistency means is it preserves some invariance. And consistency really in SQL-based systems is typically enforced by the sort of the SQL language or the SQL system. The simplest kind of invariants are like primary key constraints. So I can say every table has a primary key. There will be no duplicate primary key. That's an example of a consistency property that the database might enforce for you. E.g., no duplicate primary keys. There are, of course, more complicated ones, like, for example, most database systems provide this notion of a trigger that says after every time a record gets updated, you can check to verify that that update preserves an arbitrary programmer-specified invariant. So, for example, I can say no employee makes more than his manager. Okay? So if I want that to be a consistency invariant that my database preserves, I can create one of these triggers that every time an update happens on an employee record goes and verifies that that employee makes less than or equal to the salary of his manager, and if he doesn't, it rejects the transaction. Okay? So these are just sort of invariants that you might want to hold over the database. Isolation and atomicity really go hand in hand. Isolation is just very much like this atomicity property, saying that concurrent operations can't see each other's intermediate state. I think that, probably I wouldn't, if I were making up this acronym, have included A and I, just, it's spelled a nice word. So A and I really are doing very similar things to each other. Isolation is sort of a given if you have atomicity. So isolation just says concurrent ops, concurrent transactions. So I'm going to abbreviate transactions as X actions on the board, but concurrent transactions can't see each other's partial results. Okay, and then durability finally is this property that says that when the system says that something is committed, when it says it's done something, it really means it's done that thing, meaning that even in the presence of a variety of different types of failures, operations will persist after transactions commit. So okay, and we'll talk about how we make operations persist across failures in a couple of lectures. Okay, so really today what we're going to focus on is atomicity and isolation. How do we provide this abstraction? What is the basic abstraction that transactions provide? And then how do we actually implement this notion of isolation, this property that when we have concurrent transactions that are running, they don't see each other's partial. Okay? And then later we'll focus on durability, and we're not going to say much about consistency to some with it. Are there questions about this? How many of you guys have seen ACID before, just by show of hands? So like everybody feels like they've had at some point in some class you saw somebody say something about ACID. That's good. Okay, so just to recap, let's kind of talk about why we might want transactions. So as a programmer, just think as I write a program. The sort of abstraction that I have a complete machine all to myself and I can do whatever I want on it, and I'm not going to be, I'm not going to have to worry about what's happening concurrently is a very powerful one, right? So if I have a database, suppose I have some object A, so I read this object A into some temporary variable t, and then I increment t equals t plus 1, and then I assign, write that back into the value A, right? A completely trivial program. Imagine here that A is a database record, right? I write this as a database programmer. It looks like this is correct, right? I have a belief about what's going to happen in my head if I do this. But if some other operation, if there's some other concurrent program that's running that happens to sneak in here, and like, for example, write the value of A right here, or change the value of A right here, what ends up getting written into the database could be pretty weird, right? And I don't want I'd like to have some guarantees about what happens when these things are happening concurrently, or if there are other operations that are happening concurrently. Like I might want to group these into a block that says these things happen, all together, as opposed to, allowing these kinds of interleaved things to happen all together. All right, so this is really what isolation is about. The programming model for isolation is pretty simple. In a database, you basically write begin transaction. That declares that all the statements between this and the end of the transaction are going to be grouped together into one of these atomic isolated blocks. And then you can just write whatever you want. You write select xxx, you say update y. You do whatever you want, as many updates as you want, and then you say commit. Okay, and when you commit, all the effects of these statements, all the changes you make in the database as a result of those statements are made visible to the other transactions that are running concurrently in the system, and other users can see them. Okay, you can also abort or roll back if you want. You can say, oops, I didn't want to make those changes, undo all of them, and that's sometimes useful because you start making some changes and you realize that what you're doing is wrong or something, and you can force it to roll back. Okay, so just to make a few things clear about the way that SQL actually does this, there's some nuances about what the specific specification is that SQL provides. So first of all, the first thing is that no other transaction sees intermediate updates. The second one is that you see your own updates, which seems like a nice property, but isn't always trivial to provide. So when you do this update, if you do a subsequent select, you'll see the reflex of the effects of this update within this transaction block. So if you log into the pSQL shell, type begin transaction, do some stuff, you'll see your own updates. And then the third kind of relevant property is one about the semantics of what commit means. So you have to think a little bit carefully about commit. What the system means when it says commit is that when you issue the commit, the operation is not actually committed until the system says OK back to you, right? And we're going to exploit that trick a little bit because the system is going to be able to do some work at the time you say commit. And if it doesn't get to the point where it says OK back to you, then you have no guarantees about the thing actually being persistent. But if it says OK, the thing is persistent. Okay? So ACK of commit is what means you've got durability. Okay. What else do I want to tell you about transactions? Okay, and then the last one, the last sort of relevant point that database systems provide is that it actually turns out, and again, this is going to turn out to matter later in sort of a nuance, it's okay for the database system to, until it has acknowledged a commit, it's always possible that the database system can preemptively or sort of on its own decide to abort the transaction. Okay, so you might be running along and it's possible, it's not supposed to happen very often, but the database system is allowed to, in certain exceptional circumstances, say, uh-oh, something bad happened and abort. Okay, and this is going to turn out to matter in cases where there's deadlocks or other things in the database system. It may be required to abort some outstanding transactions. Okay, so abort is, this is DBMS can abort whatever. So as an application programmer, this kind of matters as an application programmer because to really have correct database execution, you have to be prepared for the case where you're in the middle of running your transaction and the system says, uh-oh, your transaction is aborted, and you have to do something to retry. Okay? So this is kind of the SQL level interface that databases provide. So now what we're going to do is talk about how we can implement this, what we really mean by this notion of isolation, and how we can implement this model. All right? Are there questions? All right. So this feature, these transactional things, just to give you a couple of sentences of history, this stuff was largely worked out in the late 60s. People started developing these customer information management systems to do this stuff. Probably the person who's best known for that, so there's these airline reservation systems, like Sabre, which was the American Airline reservation system, one of the early big computer systems, had some notion of transactions in it. Most of this stuff, the really details of what we're going to study now, and a lot of the formalisms and underpinnings were developed by Jim Gray in the 70s as part of the System R project. And he essentially won a Turing Award for really writing, not that some of these thoughts hadn't been had before, but really writing this all out in a very thorough way, and in a way that was principled and everybody could understand. And so he really deserves a ton of credit for figuring out a lot of these details. That, again, happened in the mid-70s at IBM. Okay, so, all right, so our goal in isolation is this, isolation and atomicity. Our goal is to take this sequence of operations, like we've written out here, any of these sequence of operations, and make it look like it all happened, or at least make a sequence of ops here. Okay, so we want to take this sequence of operations and make it so that other things aren't going to see them. So what's going to be the easiest way to do this? What did we talk about last lecture in this HStore system? What's the brain dead simple way to build a system that provides atomicity? Okay, you just run single threaded, right? Great. You run one thread of operation, it picks up a transaction, and runs it to completion. Okay, that doesn't necessarily provide durability, but it certainly provides this notion of atomicity, because you're not going to see no other operation. You're not going to have any concurrency, so you can't have this this problem. You can't have any observations of an intermediate state. So. Yeah.
Wait, that would provide isolation. It wouldn't provide atomicity, but because you could still partially do something.
Well, so it doesn't provide. Right. So atomicity, it kind of bundles in this notion of it should never be possible to observe that something is partially done, and that is a guarantee that should hold across system failures and crashes and other things like that. Right. So it doesn't provide this. It's sort of true that it wouldn't provide this ability to roll back partially completed things, for example, in the event of a system crash. But it clearly provides this isolation. It provides atomicity from the point of view of an external observer when things are not crashing. You can't tell that some intermediate thing didn't happen, if that makes sense. And we'll come back, of course, to how we provide durability and how we provide recover a database system in the event of failure. So we'll talk a lot more about that. Okay, so of course, the problem with one thing at a time as we discussed last time, there are a couple of problems with it, right? So one problem is that we can't support long-running operations. Or if you have long-running operations, they would be really bad, because then the system would be unusable for short operations, right? So if you have things that take multiple seconds or minutes or whatever to complete, then you're going to be locking the whole database system during that time, and that's not going to be very useful, right? So you could do what HStore did and say you can't have long-running operations, but obviously in a completely general world, that's not a really very appealing solution. Okay, the other sort of problem with this, as we discussed last time, is how to exploit parallel hardware. Right, so I'd like to have multiple cores working to process multiple transactions at a time, take advantage of the fact that I have this fancy modern machine with lots and lots of processors in it. And of course, again, you can take the HStore perspective and say, well, we'll just somehow figure out how to partition this into a bunch of little mini databases of shards or whatever you want to call them, and we'll run one processor per shard. But again, as we discussed last time, this isn't necessarily a completely general solution. It's not going to work in all cases. It might not be possible to apply this sharding technique to every possible system in the world. So what we want to do is develop a kind of more general abstraction that works all the time. And what we'd like to do is to allow concurrent operations. Okay, so this would be one way we could do this. The other thing is we could allow concurrent ops, and then implement a protocol, which we'll call a concurrency control protocol. Okay, which enforces some kind of guarantee that looks like that it is this, is atomicity or isolation. Okay, and this protocol, as we're going to talk through it, this protocol is necessarily going to kind of encompass, for the reasons we've already discussed, it's necessarily going to encompass not only the how do we protect running operations when, sort of in the normal case, but also how do we deal with the case where there's faults or where you need to recover or there's a crash. Okay, so concurrency control is often talked about sort of in conjunction with recovery. Okay, and the little paper that I assigned, the overview paper that I assigned by Franklin, sort of is really a discussion of the kind of canonical way that relational database systems implement concurrency control and recovery using locking and locks. And we're going to talk about that in the next few lectures. We're going to outline sort of that design, and we'll contrast it with several other different approaches that people have developed for doing concurrency control, and also look at other concurrency control protocols that don't work exactly the way SQL systems typically work. All right, questions? Good? Okay, so before we move forward, we need to kind of we had this correctness criteria here, which was like, we're only going to run one thing at a time, and it feels like, clearly that seems to provide this notion of isolation. But when we're running multiple things at a time, we need to be a little bit more careful and actually define what we mean by a correct, we're going to be running these things at the same time, we're going to be interleaving them together. What's a correct interleaving? What do we allow? Okay, so, so the correctness criteria that we're going to have is what we call serializability. We're going to define a couple of different types of serializability, but the sort of intuition is that we want, when we run these things in some interleaved fashion, we want the result to be as though we had run them in some serial order. Okay? So by serial order, I mean, we ran all of transaction A, followed by all of B, followed by all of C. Okay? And we're not actually going to run all of A, followed by all of C, B, followed by all of C, but we're going to, the outcome should be as though we did. Okay? And what we're going to do is develop these protocols that ensure that, in fact, we achieve that outcome, even when we interleave these operations together. So we want the outcome is the same as running. Our goal is, the goal is to have the outcome be the same as running the transactions one at a time. All right, so let's look at an example just so we kind of understand what would be serializable and what wouldn't. So suppose we have two bank account transfer operations. Okay, so what transfer does is it reads into some variable T1 the value of some bank account A. Okay, and then it says it deducts amount from A, so then it says A gets T1 minus amount, and then it adds that amount to some bank account B. So we say T2 gets B, T2 gets B, and then B gets T2 plus amount. Okay? So that's a bank account transfer. And I write it in this sort of funky way with these temporary variables so that we can reason a little bit about, we can separate out the reads of a variable like A from the writes of a variable like A. Okay? All right, so now imagine we have two of these guys running concurrently. Okay, so T1 and T2. And so the way we're typically going to abstract these transactions is we're going to take some program that's sort of written like this in a programming language, and we're going to think instead just about the reads and writes that these transactions provide. So we would actually summarize this transfer transaction as, a read of A, followed by a write of A, followed by a read of B, followed by a write of B. Okay? I've noticed that we've abstracted away all of the sort of computation here. In particular, there might be arbitrary dependencies between this read of A and the values that we write into A or B, right? Like, the fact that we wrote into A something that depended on the previous value of A, it's sort of lost in this schedule. But by thinking about things in terms of this schedule, it's going to kind of simplify our notion of what we mean by serializability. But you have to realize that like this write of A could depend on anything we read before this, and this write of B could depend on anything we read before this. All right, so okay, so now let's consider an interleaving of these operations. Suppose I run two transfers, T1 and T2, okay, which are an A, B, and $1, and A, B, and $1. Okay, so I'm going to do two concurrent transfer operations. And let's suppose I start with, say, A is equal to 5 and B is equal to 5. Okay, so we take this very simple example. A simple possible interleaving of these might be read of A, write of A, followed over here in T2 by read of A, write of A, and then read of B, write of B, and then read of B, write of B. Then read of B. Okay, so this is an interleaving. Is this interleaving serially equivalent? What do we think? Is it serializable? Well, we can kind of figure it out by doing the math, right? So this guy's going to read 5 here, write 4 here. This guy's going to read 4 here, write 3 here. This guy is going to read 5 here, write 6 here, and this guy's going to read 6 here, write 7 here. Okay? So in fact, what we see at the end is that the balances are, 7 and 3, exactly as they would be if we had run these things in some serial order, right? And if you look at all the reads and writes that happen, you can see that the reads and writes that happen are sort of equivalent to running T1 followed by T2. Okay, so the simplest kind of definition, intuitive definition of how we define whether a particular schedule is serializable or not is just to look at all the reads and writes that happen, or all the reads that happen, and confirm that all the reads were equivalent to what they would have been in some serial schedule, and to confirm that the kind of final state of the database system at the end of this is also equivalent to what it would have been in the serial schedule. That's what's known as view serializability. We'll define it again in just a minute. Okay, so let's take a different example though, one that's not serializable. So a not serializable example would be something like T1 does read of A, T2 does read of A, T1 does write of A, and then T2 does write of A. Okay, and you can immediately see what's going to happen here, right? Which is that these guys both read before either of them has written, and so we're going to end up kind of clobbering one of the writes. So here this guy's going to read 5, this guy will also read 5, and then we'll write 4 and 4, and so the end state that we have is not serial equivalent. Okay, so we kind of interleave these operations in a bad way, right? So clearly we can't just arbitrarily interleave these things. We need to do something that prevents these kinds of bad interleavings from arising. All right, so that's what concurrency control really is about. Okay, so before we define our protocol, today we're gonna work through this locking-based protocol for concurrency control. Before we do that, I just want to come back a little bit to this notion of how do we test whether a given schedule that we see is serializable or not. Okay, so we have we need to define a couple different types of serializability and then talk about how we test them. All right, so the sort of most intuitive definition of serializability is the one that I just gave you. It's this notion of view serializability. So it says that an ordering of these instructions like this here is serially equivalent if and only if for every value read in the schedule, like this schedule here, there's some serial schedule, S prime, where it goes all of A and then all of B, or all of B and then all of A. There's some serial schedule S prime where every value that we read in S was the same as the value we read in S prime, and where the final values that we wrote out in S were the same as what the final values that we wrote out would be in S prime, if that makes sense. So this is hopefully a pretty intuitive definition. And kind of given a schedule like this, it's a schedule of just a couple of transactions, it's not too hard to test for it. It turns out that deserializability doesn't really get used very much in practice because we don't have great protocols for sort of enforcing view serializability as we run. So we can test the schedule to see if it's view serializable, although actually the testing of it is sort of exponential in the number of the number of concurrent transactions that are running. So it's described as being NP hard, although in reality probably you're not actually you're gonna be running small numbers of concurrent transactions. So I'm not sure the fact that it's exponentially hard to test for is hard, but it's what's bad about it. What's bad about it is that there's not an obvious protocol that will use view serializability to sort of prevent bad schedules from arising. So what we want is sort of this concurrency control protocol that can let us sort of arrive at good schedules. And so we need a slightly different definition of serializability in order to do that. And that definition is called conflict serializability. So and what conflict serializability does is it defines a notion of operations that conflict, and then the definition is based on basically not allowing conflicting operations to occur. Okay, so a conflict, really all a conflict and conflict serializability means is that transaction 1 reads some variable that transaction 2 writes, or transaction 1 writes some variable that transaction 2 reads, or they both write the same variable. Okay, and the sort of notion is that in any of those 3 scenarios, you can end up with this kind of some bad situation happening where things can get the writes can sort of clobber each other, like we saw in this example here, where these 2 writes, because these guys both read A and write A, the 2 writes can kind of get in each other's way, and you can end up with an inconsistent state. Okay, if both databases just read some variable, like both transactions just read some variable, like transaction 1 reads A and transaction 2 reads A, that's not a problem. It's not a conflict because these 2 operate. That's not going to affect whether or not there's a serial equivalence just because they read it. They also have to, there has to be a write that happens. So a conflict is either, if you have 2 transactions, T1 and T2, T1 and some variable A, T1, can write A, T2 reads A, T1 reads A, T2 writes A, or T1 and T2 both write A. Okay? So those are the types of conflicts that can occur. By the way, when I talk about these, we've been sort of talking about these abstract variables like A and B, which obviously are meant to represent, in this example, bank account balances. You should think, and we'll talk more about what the sort of granularity of these objects is and why the granularity matters in a couple of lectures. But for now, sort of think about the granularity of these objects as being like records in a database, right? Like a bank account balance, the record of one bank account in a database system. But conceptually, actually, everything that we're going to say is going to hold whether these things are, records or entire tables or fragments of tables or pages on disk. And we'll talk a little bit about how that works in a couple of lectures. And in fact, these objects are pretty abstract and can be sort of anything that's stored inside the database. But for now, it's best to think of them like we sort of have in this example here as bank account balance. Okay. All right. So then our definition of conflict serializability is as follows. We say a schedule is conflict serializable if we can take non-conflicting operations and swap them with each other in order to derive a schedule that is serial. Okay? Or put differently, for all pairs, this means that for all pairs of conflicting operations, operation 1 and T1, operation 2 and T2, either O1 always precedes O2, or O2 always precedes O1. Okay, so if we come over here to our example, you can see what we're kind of getting at here. So if we look at all the pairs of conflicting operations, right? So here, this read conflicts with this write here, right? But you can see that in this case, T1 precedes T2, right? And here you can see that this write conflicts with both this read and this write, but you can see that this write precedes both this read and this write in T2, okay? And so this swapping thing basically is saying that I can take this block of transactions, which doesn't interfere at all with this block, these two statements, which don't interfere at all with these statements, there's no conflict, and I could sort of move them up, and then I would end up with a serial equivalent schedule T1, T2. Okay? So you can see that the equivalent schedule in this case is T1, T2. And I sort of can see that because I can see that these operations don't conflict at all with these, and so therefore we're good to go. Right? So these are two sort of ways of viewing complex serializability. And if you look at this example here, you'll see that it doesn't, this test that we have at the bottom doesn't hold. So read A here precedes write A here, right? But write A here comes after read A in transaction 2. Okay, so this test that we had at the bottom that said that they should always, either all of T1 should precede, all the conflicting operations in T1 should come before the conflicting operations in T2, or vice versa, that test failed in this case. So this is not a complex serializable schedule. Other questions? Okay, so the nice thing about this is that we're going to be able to define a protocol that actually enforces conflict serializability, right? So before we define that protocol, though, I just want to sort of talk about how we can test to see whether a given schedule is conflict serializable. This is like a great quiz question, so you'll probably get to do some examples of this. I'll promise at 3. So how do we test for this? Well, one way we can test for it is to see if we can apply this kind of swapping thing. But another way that we can test for it is to make what we call a precedence graph, which sort of tests this second rule here. So we can either try to do the swapping thing, or we can do this precedence graph thing, which really is basically embodying the second rule that I just showed. So given two transactions, Ti and Tj, we draw an edge from Ti to Tj when there's a conflict. Okay, so if Ti reads some variable A before Tj, reads or writes some variable A before Tj writes it, or Ti writes some variable A before Tj reads it, then there's we sort of draw an edge, and that's a conflict. So in this case, for example, we've got two transactions, T1 and T2. Okay, so here we say if T1 reads some A before Tj writes A. So here T1 read A before Tj wrote it, we would draw an edge. Okay, and then similarly, if T2 reads something before T1 wrote it, then we draw an edge this way. Okay, so we make a graph like this, and a cycle in this graph implies that this is not conflict serializable. Okay, so cycles are not serializable, not conflict serializable, to be precise. I'll write it more neatly, sorry. Cycles implies not conflict serializable. Okay, does that make sense? Do you have questions about that? And again, it's really just very much by, this isn't a super hard test to do. You can kind of look at these things and just apply these rules like I put at the bottom of this thing here. Okay? All right, so let's take a 4-minute break. We'll come back at 3:16, and then we'll talk about how we actually implement a system using locking that provides conflict serializability. So I think so maybe you can stick these. You put a button in there. Otherwise, they're sort of slightly different because they normally require. I normally think of those things as a process of multiple processes executing something like that. So linearizability, I think linearizability, do you remember, is linearizability is stronger than transactional consistency? And then sequential consistency is weaker than linearizability. Why is it weaker than linearizability? Because
linearizability requires that linearize
you can move stuff around, but all you're saying is that it's a move that I see. Okay, I have to go look. These things are all related. There's a larger theory of consistency that can relate all these things together, but I haven't thought about it enough recently that I'm likely to say something that's going to be wrong. So I'm sure that there's a very good Wikipedia article that relates all these things together. I mean, they're very closely related, and the differences are subtle. I have to go. There's somebody.
Oh, career. The ticketing. I just did the extension to one of the. Oh no. I did the it's like a file system.
Oh yeah,
It's one of the ones they give. Yeah. Implementing it was hard because the theory is it's interesting and challenging, but you can get it. But then the implementation is you don't choose good encoding schemes. Everything just breaks all the time. Like our crypto library made an encoding, and Unix doesn't like that encoding. So when you make a file with that name, it's just I don't know what happens. And then HTTP doesn't like that encoding, so sometimes the packet doesn't get through the network. So you have to be careful about encoding if you do that one. But it shouldn't have been that hard. We just didn't understand that problem until too late. So, it was fun, except
log entry on it.
I didn't sleep for 4 days because I was trying to fix it. But, yeah.
That's kind of my sense.
Yeah, but I mean, if I had to do it again and I would have had that little piece in my head, it would have been so much easier. It would have taken me half the time. Less than less than 2 days. Okay. I always avoid mobile security. Mobile security it's just in a terrible state. I mean, there's good things people are doing it, so if you want to do it,
all right, let's go ahead and get started.
I just don't want to do it.
Okay, so now we kind of understand we have this notion of schedules, we can test for a schedule, but we need a protocol that, as the database system is running, as it's reading and writing objects, can guarantee that we end up with something that's serializable, right? Like the database system doesn't, I mean, you could maybe build a database system this way, but it sounds like a bad way to build it, where you don't want to just run stuff and then after the fact test and see if it was in fact, serializable. You'd like to have the system, kind of, as it's running, guarantee that things happen in some serializable. So that would be the most sort of natural way to build the system. So before we define this protocol, I just want to point out a couple of other things about transaction schedules that really actually sort of relate to this recovery property that aren't strictly about serializability. So let me just draw a couple of other schedules on the board and then we can talk about them. Okay, so okay, so let's look at this example. So this example is T1 reads A and writes A, then T2 reads A and commits, and then T1 reads B and aborts. Okay, so by the definition of serializability, conflict serializability, this schedule is serializable because the only conflicting operations are between this write of A and this read of A, and all the operations of T1 precede all the operations of T2. But what's kind of terrible about this? Or what seems bad about if I actually allow this to happen? Yeah? Yeah, so it's kind of bad because now if this write A, if this guy read this version of A and then committed and told the world about it, right? And then, so some other transaction maybe saw this value or something, I don't know. Then this guy comes over here and he aborts, then, this, it's not really possible to go back and undo the effect of whatever this T2 was, because it's already been released into the world. And yet, that value that he read shouldn't have been visible to the world. So it seems like this kind of, it's not very attractive, to have a system that doesn't provide this property. So we call this property recoverability. Okay, and it really means that you basically never read, the transactions never read uncommitted values. Yeah? No, this is a form of isolation, right? I'm just pointing out that simply being serializable is not sufficient to provide, is not actually sufficient to provide this kind of recoverability property, right? And for isolation purposes, this only matters when there's one of these aborts that appears here, right? Like if this transaction hadn't aborted, we all would be well, we wouldn't have a problem. It's just when this abort happens, then it introduces this kind of problem, right? Okay, so let's look at another example. So suppose T1 does a read of A, T2 does a write of A, T1 does a write of A. Oops, sorry, wrong example. T1 then does a write of B, followed by a write of A. T2 does a read of A, followed by a write of A. And then T3 does a read of A. Okay, and then T1 aborts. You guys probably can't see this down here, but then suppose after all that, T1 aborts. Okay, so this is actually, it's almost the same as this recoverability situation, right? But these T2 and T3 haven't committed yet. So they're not committed, but we have this problem that now T2 and T3, they've read some stuff that T1 wrote, right? And so when T1 aborts, we're going to have to, basically the only choice we're going to have is to sort of undo the effects of T2 and T3 somehow. Typically the way we do that would be to abort T2 and T3. Okay, so this is what's known as a cascading abort or a cascading rollback, and we might like to avoid it. Okay. So we can avoid this unrecoverability property by not allowing T2 and T3 to commit until T1 commits, but in order to prevent this cascading abort, we can't actually allow these reads to happen at all. Okay? All right, so now that we have these definitions, now let's actually define our protocol. So our protocol is this locking protocol. This is the protocol that was presented in the paper. You guys, since you have all seen transactions before, have probably seen some form of transactional locking, but let's just review it, okay? So basically what the locking protocol does is to codify this conflict, this notion of conflict serializability. So specifically what we're going to do in our locking protocol okay, it is before every read, acquire a read lock, okay? And then before every write, acquire a write, sometimes called an exclusive lock. And sometimes we'll call these read locks shared locks. Okay? And the reason we're going to differentiate between these two kinds of locks, right? So every time we read an object A, we'll acquire a read lock or a shared lock. And every time we write an object A, we'll acquire a write or an exclusive lock. Okay? Yeah?
Does the every mean for each read or for all reads?
It means for each read of an object, we have to ensure that we're holding the lock. Okay, so I haven't yet said when we release these locks yet. Okay, so don't think of this as, remember these are these transactional locks, we're going to hold them for a long time. So don't think of this as acquire the lock on A, do some operation on A, and then release the lock immediately. It's like acquire the lock, and then sometime later, which we're going to define in a minute, we're going to release that lock, but we're not going to release it immediately. And that's going to be the sort of key to this protocol, is that we don't release the locks actually immediately. And so just before every read, we have to make sure that we hold the read lock. And before every write, we have to make sure that we hold the write lock. Okay? And the reason we differentiate between these two is because this is sort of what conflict serializability is about. We are allowed to have multiple transactions holding a read lock at the same time, but we're not allowed to have multiple transactions holding a write lock at the same time. So we can talk about lock compatibility. Okay, and if we have, imagine here's T1 here, or here's T1 and here's T2. Okay, so T1 holds a shared lock, holds a read lock on some object or a write lock on some object, and T2 might hold a read lock or a write lock on it. Okay, if T1 and T2 both hold a read lock on some object, that's permitted. But because we're not going to allow T1 to hold a read lock on an object while T2 holds a write lock on it. Similarly, we won't allow T1 to hold a write lock on an object while T2 holds a read lock on it, and they can't both hold a write lock on an object. Okay, so when I put an X here, what that means is if you think about this, the execution, the transaction is going to kind of chug along. When it goes to read some object A, it's going to attempt to acquire the lock. Okay, if nobody else has the lock that it needs, good, it can acquire the lock and proceed, okay? Just like in a regular locking protocol. However, if another transaction is holding a lock, then it has to consult the lock compatibility. We use the lock compatibility rules. So if it wants to acquire a read lock and another transaction has a read lock, that's permitted. But in any other case, it's not, right? So if it wants to acquire a read lock and another transaction has a write lock, that's not permitted. If it wants to acquire a write lock and another transaction has a read lock, that's not permitted, and so on and so forth. Okay, and when I say not permitted in this locking thing, if lock acquisition fails, then we wait. Okay, just like in a conventional locking, a mutex-based locking protocol. You try and get it, you can't get it, you wait until the lock is free. Okay. Now, there's one last little thing that we need to define about this locking protocol, which says that if T1 holds a read lock on something and then it wants to later write it, so it read A and then it wants to write A, and nobody else is concurrently reading A, then it's allowed to upgrade from a read lock to a write lock. Okay? Upgrades are allowed within a transaction. But if it has a read lock and somebody else has a read lock, it's not allowed to upgrade. It has to wait until that. It has a read lock and wants a write lock. Somebody else has a read lock as well. It's not allowed to do that. Okay? Okay, so far so good. So we've got a basic locking protocol, but we haven't said anything about when we can release locks. All right, so let's kind of see what happens if we try. You might think, well, what if I just release a lock immediately? Okay, so let's come back over here to our schedules, right? So what this sort of says is, imagine this situation here. So transaction 1 reads A, right? But if it were to release this lock, so before it reads A, it acquires a read lock on it, right? If it were to release that read lock, even for a moment, and then go and acquire this write lock, right, then we sort of would be in trouble, because at that exact moment that we released this read lock on A, T2 could have snuck in and read A, and then we would be in this situation up here, right? And so we can't, it's actually not okay for us to release these locks as we're running along. We have to hold on to the locks until something. Okay? So how long do we have to hold on to the locks for? Well, we have to hold on to the locks until we have finished reading all the objects, finished acquiring all the locks that we're going to need. Okay? So I can't release my first lock until I've acquired all the locks that I need to complete my transaction. Okay? So at this point, basically, right here, this is the point where T1, we call it its lock point. Okay? And you can see, at this point, it's not going to need to acquire any more locks in order to complete. And so it's never going to be possible for T2 to sort of do this thing where it sneaks in and does some little update underneath the covers and messes this up, right? So I can start releasing locks once I release this lock point, as long as I guarantee that I'll never acquire any more locks from that point. Now, that doesn't mean that I can't modify some objects after the lock point. I can do some work after the lock point, like I could, I might release the lock on B here and then go update A. That would be okay, because you would know that once you reach the lock point, you would never need to make a modification or even read B again. So you're sort of done with B once you release the lock point, if you reach the lock point and you release the lock point. Okay? So this protocol, where we acquire locks until we've acquired all of our locks, and only then do we start releasing locks, is called two-phase locking. So the two-phase locking protocol says we release locks only after acquiring all the locks. Okay, and the moment when we acquire all the locks is our lock point. Okay? And this is sufficient to ensure conflict serializability, because you can, and if you kind of want to think about it in this case, right, this transaction acquires this read lock here, right? And some other transaction at that point, we know that some other transaction is, we're going to be able to make our reads or updates to this value A, and no other transaction is going to be able to sneak in and update it underneath the covers, right? So now it's possible that some other transaction can sneak in and make some modification to B while we're making this modification to A, and then when we try to modify B, we won't be able to get the lock on it, and we'll have to wait for that transaction. And there's an even worse situation in which that other transaction might have then gone on and tried to get a lock on A. So we're holding a lock on A, and it's holding a lock on B, and then we've got a deadlock, and we're going to have to figure out how to deal with that. But this protocol is sufficient to guarantee, it's prone to deadlocks, but it is sufficient to guarantee that we'll end up with this conflict serializable schedule in the end. Yep.
So you can only release locks after the lock point?
Yes, you may only release locks when you release locks. Okay. Good. Yeah.
We're saying it's lock point, is that the end of transaction 1 or is it?
In this particular case, the lock point is after it has acquired all of the locks. The lock point is just the point that you've acquired all the locks. So for transaction 1, it's when that last acquisition, and it's defined on a per transaction basis, and it's that point where it did the, it acquired its last lock. Not really, I guess actually, to be technically correct, it acquired its last lock just prior to this writing B, right? So prior to writing B, it acquired an exclusive lock on B, and that was when it reached the lock point. That was the last lock, the last thing it acquired. And at that point, it can't lock any more objects, but it can start releasing. It can start releasing locks, but once it starts releasing locks, it can't acquire locks on any more objects.
But before it acquires the RB locks, it has already executed the write A, right?
It's right. So the sort of way to think about this is we're going down in time, reading A, writing A, and so on and so forth. So the protocol says read A, acquire a lock on A, read the value of A, acquire exclusive lock on A, write A, acquire read lock on B, read B, acquire exclusive lock on B, write B. So we need to precede every attempt to access an object with a check to verify that we hold the lock on it. Just like if you're doing, concurrent programming with mutexes or something, right? You have a mutex that protects a variable, you always acquire that mutex before you enter. There's a critical section that protects variables that are accessed by multiple threads. The difference here is that we're not, unlike in a mutex where you release the lock as soon as you exit the critical section, you're going to hold this lock for the duration, or at least until the lock point.
I guess I'm just asking because this meaning section is not really concurrent because we can't even do anything in 2 until after 1.
Okay, so for this particular case, obviously it's very simplified, right? Because like this schedule, for example, that I'm showing here wouldn't it wouldn't actually, you couldn't achieve this schedule using, even though it is serializable, you can't achieve this schedule using this locking protocol that I just described, because you're going to acquire the locks on A, and then transaction 2 is going to sit there waiting to get its locks on A until we start releasing them, right? So this protocol couldn't actually result in that schedule that I've shown there. But there are other concurrent things that could happen, right? Like transaction 2 could have done something to some object C that it didn't care about, that transaction 1 doesn't touch at all, right? So it's really only the operations of these objects that are accessed by multiple transactions. Does that make sense? Okay.
We all using something like semaphore.
What's that?
We all using semaphores.
So the specific implementation of locks, you guys will build this in Lab 4 in SimpleDB. Typically, so you're going to need to do lock acquisition itself is going to need to be protected by some kind of a mutex, right? Like when I'm going to have some table basically that's going to record the locks that every transaction is holding, and in order to update that table, I better be sure that I'm the only transaction that's actually writing to this this lock table that says that I have a lock on object A. And I could use semaphores to implement that sort of that operation, that update to this table. Okay, so this table is itself a shared concurrent object that all of the transactions and threads are going to be kind of dependent on, right? And if you want to think of this as a sort of every transaction is running in its own thread, that's sort of what we'll do with SimpleDB. We'll create a thread per transaction, and there'll be this shared data structure that's the lock table. That lock table will be protected in Java. You can just make this some serializable, put the serializable block around it, and then you will have threads sort of write into this lock table when they attempt to acquire the lock or release the lock. Okay. More questions? Questions are good. So, yeah. Okay, so yeah, you're right. In this case, if I had released the locks on A, then it might seem like I'm okay. But the problem is, if I release my locks on A, right, then I'm going to later have to make these modifications to B, and this.
The right to B could depend on your read of A.
Right. Well, right to B could depend on your read of A. Yes, that's true. So what that would allow is somebody else could, come in and do like if transaction 2, if I released it, then I could have this situation like transaction 1 does read of A, right, of A. Transaction 2 does, what's that?
You can really lock that position, require A, let it go, somebody else can do it, require A, do something.
Right, I mean, but so the specific, like, you're sort of right in this specific, I mean, so it's, the concern is that if I release the lock here, then somebody else, at any point I release the lock, somebody else can sneak in and make some modification or update to A, right? The question is, if I knew that I'm done with A at this point, right, would it be okay to release, why isn't it okay to release the locks on A at this point, because I'm not going to do anything else with it?
You're right.
And I think the intuition is sort of what was said, which is that, you know, then somebody else can come along and, you know, my right to A depends on this, my right to B might depend on this value of A that I read.
So you don't want anyone else to write to A in the middle. Right?
And if somebody else, I'm just trying to think through the example, somebody else writes to A in the middle, like this transaction over here does read A and write A in the middle of that.
We already have the value of A that's saved on the
But if both the transactions write to B depend on their reads to A, then if they're both like incrementing A and setting that value to B, you could miss that increment.
If they roll back, they roll back.
If you're setting like B to A plus 1, it should be set to like.
Sorry, so you're saying, like, I mean, I'm not sure that this is the case. You're saying B here gets A plus 1, right? And now the problem is that somebody else comes along and can...
or B plus A plus 1 or something. Yeah.
What's that?
You have to wait for a lock on A if you want to do that. If you want to let B equal to A plus 1, you apply a lock on A back.
Right, but the example is saying, well, like, what if you just remembered that you had written this value or something like that? I think that
Does it violate recoverability?
well, we'll come back to recoverability in just a minute. But
So if the update to B was impossible,
what's that?
if the update to B was impossible, then you would have minus something from A's account, but not added it to B.
Sure, but the update to B, like whether or not you could do this right to B,
Yeah, if you try to increase B's value by A in both of them, you're only going to end up increasing it once instead of twice, if you allow for that.
if you try and increase B's value,
By A,
so
Then-
you're saying that what this does is say B gets
B plus A,
B plus A, okay?
and the other tries to do the same.
Yeah,
What you'd expect at the end, if it was serializable, would be B equal to like B plus 2A, but in this case, you would just be setting it to B plus A at the end, if you release your locks on A.
right, because, so the problem essentially is that somebody could sneak in and do if I release my lock here, then this guy comes in and reads the value of A and updates it, but you're saying that I use that value of A, that, you know, the previous value of A in subsequent commutations, and so that's not serialized. Okay, good. So that's an example. I think there are simpler examples of this, but I think that is an example of why. Do you see why that would be the case? So we write this value here. This value A that we wrote depends on, you know, this value of A that we wrote sort of depends on whatever value of A we wrote up here, right? And, you know, somebody else might come in and do the same thing, and now he's gonna
But in that case, you would have to require a read lock on A again, like,
okay, so if I acquire a read lock, if I'm willing to acquire a read lock on A again, then
Reading uncommitted data.
okay, but and so yeah, I mean, so this will become clear. I mean, whether or not this schedule is not going to be allowed for different reasons, but I'll come back to you guys with a better explanation for why this isn't even allowed in two-phase, basic two-phase locking. This observation that you guys are having about this thing isn't recoverable is the other problem, right? So the other problem with permitting this schedule, if I were to permit this schedule, is that because this right A here is not committed, this guy reads it, and now if this guy crashes, then we're in trouble. We have this cascading property, or this, even if we allowed this guy to commit after reading it, then we have this abort property, the recoverability property that we wanted to avoid. Okay. Okay, so let's come back to this. So this basic two-phase locking property actually, this property that we wrote out here, which is that you only release locks after the lock point, is not sufficient actually to provide this cascadelessness property. So let's see an example. Okay, so if T1 does read A, write B, okay, it is at this point, it has now acquired all of its locks, right? So T1, and then suppose maybe later down here it does some other read of A and write of B, okay? So this is the lock point, and then it does a commit. Okay, so this is the lock point. Right, so we might say that it's okay, according to the two-phase locking protocol we had before, it would be okay to release locks, start releasing locks at this point. But you can see that the problem with releasing these locks here is that, what if this guy ultimately aborts, right? If this guy aborts, then some other transaction might have come in here and, like some other transaction at this point just before we aborted, or just after this last read of A might have snuck in, right? So if I released, imagine I release A here, then right after this read of A, because I reached my lock point, so I'm allowed to release A by the two-phase locking protocol. At this point, this write B, somebody can sneak in and read A here, okay? And the problem is that we then abort, right? So this two-phase locking protocol is not recoverable. Okay? So what we need to do in order to make it recoverable is ensure that we don't release locks on things we wrote until after the end of the transaction, right? So if we hold on to this lock until if we hold on to anything that we wrote, if we hold on to the locks until after we make the commit or abort decision, then you can see that we won't violate this recoverability. We will be able to have recoverability because we can avoid this situation where we did this release of this lock and some other guy snuck in and read some uncommitted value, right? So if we, the fix is to hold right locks until and the reason that this works is because basically this lack of recoverability results when somebody else can read our dirty data, right? And so we want to prevent these dirty data reads, and the way we prevent these dirty data reads is by holding right locks until the end. Okay? So this is what's known as strict two-phase locking. Strict 2PL. 2PL is the standard abbreviation for two-phase locking. So strict two-phase locking says hold right locks until the end of the transaction. Okay, so there's actually one more level of locking, two-phase locking, which is what's actually implemented in most database systems. And it's what's known as rigorous two-phase locking. And this says hold read locks until the end as well. So can anybody see, why do you think I need to hold read locks until the end? I need to is because if you think about the way these SQL terminals get used, right? Can you imagine I'm typing into a terminal, a shell, right? I don't actually know when I acquire my last lock, right? Because I only know that I acquired my last lock when the user tells us to commit. So if the user's not giving us the whole thing up front, then I kind of have no choice but to hold my locks until the user issues the commit statement. So this is basically what most systems implement. The other kind of nice thing about rigorous two-phase locking is that in rigorous two-phase locking, I can, the equivalent serial order is just equal to the commit order of the transactions. So I can just order the commits, and that turns out to be the same as the commit order of the transactions. Right. So this is our protocol. It's basically the same as this protocol, except for that we only release locks after the transaction commits, instead of being allowed to release locks at this commit point. Okay. And you can see why in this particular example, this rigorous two-phase locking, this is clearly not recoverable. If we were to release locks at this point, we would clearly be not recoverable, and so therefore this schedule would not be permitted under this rigorous two-phase locking. Yep.
So in this model, if you only do writes, you still do not acquire read lock.
You don't need to acquire a read lock if you do writes. That's true. Why do you ask it this?
Because given that we hold everything until the end, I was wondering why you actually needed to have two different models.
Yeah, okay, so it is sort of true that at this point, well, you still need to, this still permits concurrent readers, right? So you need to differentiate because you want to permit concurrent readers, right? So, it doesn't matter. Transactions T1 and T2 can both read A, and that doesn't have anything to do with, whether or not they're allowed to commit or not. So really the importance of having the different locks is to permit concurrent read stuff. Okay, so this is the kind of protocol that the protocol that most systems implement, and it's a pretty simple protocol to implement, and you'll get a chance to practice it. There are a couple of little details that we need to work through. I think, so in particular, we need to talk about this notion of deadlocks. I think rather than telling you guys how we solve deadlocks in the last 5 minutes, what I'll do is let you guys collect your exams, because that's probably going to take 5 minutes, and we'll talk about deadlocks more next time. So.